Yeah, hello again, everyone. Welcome to Agentic AI Governance, Data Foundations, and Real-Time Policy Enforcement. So today, Murthy, Chandrapaty, and myself, William Liang, we're going to be basically going to do a quick overview of our service, PES, the Policy Enforcement Service. We'll discuss how we migrated it from Cosmo DB to Neo4j, the paradigm shift we made along the way, and how migrating to Neo4j allowed us to agentify PES and enable current and future AI workflows. Oh, before I start, a quick shout out to our colleague, Persilia Paramita, who was instrumental in helping us wire up a lot of the presentation today. Anyway, so what is data governance? If you go to Adobe Experience League, it's defined as data governance is an essential concept that's intertwined with every capability in Experience Platform. What exactly does that mean? Well, AEP, Adobe Experience Platform, is a platform that drives Adobe Experience Cloud applications, Journey Optimizer, Real-Time CDP, Customer Journey Analytics, and a core feature of AEP is data governance. This is the framework that customers use to label what data can be used and define policy for how that data can be used. And data governance is the framework that assures that that data and usage is compliant throughout the whole process as data flows into a platform on the left-hand side of this diagram, through the platform and down to the applications on the right-hand side of this diagram. One of the core services of data governance is PES, the Policy Enforcement Service. This is the service where various platform entities are registered and arranged in a label inheritance graph like this one you see here, where the properties of the resources, the labels and marking actions are represented by these rectangles. So previously, when PES was implemented on top of Cosmo DB, that led us down the path where the business logic was one where we did a brute force traversal of this graph to discover labels and marking actions. That obviously doesn't perform or scale very well. That led to high CPU utilization, high memory, high latency. Obviously, performance is a function of graph complexity. So what is graph complexity? Well, graph complexity is actually a function of three things: graph size, graph density, graph connectivity. Graph size is the number of nodes and the number of edges of relationship. Graph density is a function of local density and global density, where local density are these super nodes, kind of represented by this dark blue rectangle in the middle of the screen on this diagram, where there's a lot of relationships fanning in from the left-hand side and relationships fanning out on the right-hand side. Graph density is also a function of global density, which are the connectivity of subnodes, subgraphs. So on the right-hand side of this diagram, the orange nodes, you can see they're highly connected amongst them where the relationships are very dense. Then there's graph connectivity, which is the sheer number of paths and the depth of the path. And when you, the interesting thing is for highly connected subgraphs, every time a path makes a hop, that actually multiplies the number of paths. So migrating to Neo4j actually allowed us to address a bunch of these, basically address all of these things through a number of paradigm shifts. The first one being a structural shift, where previously the data model was one where we had these fat property-heavy nodes, and Neo4j allowed us to essentially explode the data model out so that the properties are factored out into first-class citizens, into their own nodes. That allowed us to essentially query the nodes directly and do forward and backwards traversal straight from the nodes. The other two paradigm shifts are essentially logical shifts and workload shifts, where we logically evolved from a brute force traversal to essentially intelligently pruning away large portions of the graph, so making ourselves less sensitive to the complexity of the graph. And the workload shift is moving the workload from being having expensive reads to expensive writes. So reads are now much more performant, but we do have to be more conscious about how we manage our writes and the scope of the writes. So with respect to logical shift, like I said, previously we would have a graph like this. We would have to do a brute force traversal along this throughout this graph to discover a specific label, say one of these brown nodes, and then a specific marking action, say a pink node, and to determine if there's a path between those. Now that we exploded our data models and we can query the label, the properties directly, we can essentially query for the specific label and the specific marking action. So in this example, if you can imagine, if we need to look for, say, the first brown node and the first pink node, and then just establish if there's a path between them on this left-hand side, we can effectively prune away all the complexity on the right-hand side. So regardless how large and complex the graph is, we can throw that away because that's irrelevant to what we're looking for. So essentially, we eliminate brute force traversal and simply prune away all the irrelevant parts of the graph. So having done all this, that allows us to make our reads super fast, but we do have to be careful about how we manage the writes. So we have to put the graph in the correct state in order to facilitate these writes. Now, when we talk about writes, there's three elements, three facets we have to be conscious about. One is write amplification, then there's write serialization, and write latency. Write amplification is the fan-out effect. So in this diagram, if you can imagine, an update to this pink node will fan out writes to the green nodes, which will fan out writes to red nodes, which fan out writes to the blue nodes. So we have to make sure we manage these fan-outs to limit the scope of the writes. Write serialization is imagine there's concurrent updates to several green nodes. They're effectively going to serialize around this pink node. So again, we have to make sure that we minimize the scope of the writes so we're not serializing a bunch of these things around certain nodes. And write latency is the fact that all writes go to the leader node in Neo4j Aura. So we want to make sure we minimize the workload that's going to the leader node. So how do we address all these? Well, basically, to address the fan out, we need to basically remove any unnecessary relationship. Don't be too verbose. So in this example, if there's an update to a yellow node and it fans out to the pink nodes, we want to eliminate any relationship to essentially eliminate any fan out from the pink nodes. Write serialization is again, if there's concurrent updates to yellow nodes and they all fan out to these pink nodes, we want to limit the scope. So if the left-hand side yellow node fans out to right to the pink node, but the scope is really the left pink node, we want to limit that scope so it doesn't block and serialize updates to the other yellow nodes on the right-hand side. And then again, to address latency, these writes all go to the leader node in Neo4j Aura. We want to make sure we clearly delineate reads and writes so we can direct them to the leaders or the followers so that we essentially minimize the workload on the followers. So having done all this allowed us to essentially migrate to Neo4j, really increase our performance, reduce latency, allowed us to scale, and that allowed us to agentify PES, the policy enforcement service. So at this point, I'll hand it off to Murthy and I'll let him talk about how we agentify PES. You're muted, Murthy.
Thank you. Thanks, William. Hello, everybody. I'm going to talk about, like William just showed us, how we solve the hard problem, which is the graph problem, turning into lean nodes, intelligent pruning, and a surgical search. That's the foundation. Now I want to talk about what we build on top of it. Now that governance is solved, because once you have a particular governance graph, the next question is, how do we let engineers or data stewards actually talk to it? Writing Cypher by hand to debug a policy violation at 2 a.m. is not the answer. So we built an agentic AI workflow that sits on top of this foundational graph. So the architecture is pretty straightforward, but the details matters. So a user types in a plain question in natural language. The question goes through a schema over prompting, and then I'll explain what that is in a bit. And Cloud generates a production grade cipher we execute against the governance graph, and then the results are back translated into an English natural language. The whole thing runs on LangGraph with MCP tools connected, backed by Claude on our data centers. So user types in the question and we get the results in natural language. So why the out of the box LLMs decipher fails? Because the schema awareness is the difference between a demo and a production system. If you just send a natural language question to an LLM and ask it can generate a cipher, but there's a likelihood of hallucination. It will write a match query when your label is entity. Silent wrong results are worse than errors. So it will there's a possibility of generating a silent wrong queries and translate into a wrong results too. Our solution is every prompt contains the exact AEP schema, the schema that we have, so that we inject the context and the LLM cannot hallucinate what logged in the prompt. So every query automatically scoped to the right tenant and the IMS already in sandbox. So zero cross-tenant data leakage as well. So that's the multi-tenancy safety here. The React loop, the other thing that separates this from query tool is the React loop, which actually does the reasoning and acting on, and that's not a single cipher query. So I'll show you in a bit the demo. But the agent decomposes that into multiple targeted queries, and LangGraph manages that loop using making calls to the tools. The context injection, and we did not train Claude on AEP data. Because the training is slow, expensive, and it can go stale. Instead, we did is runtime context ingestion. Static schemas context is baked into the prompt. Dynamic tenant context is injected at query time. Where this is heading in the future is towards the skills, the MD files that we do, the skills. That's the future that we are heading towards. Your schema, so the advantage here moving towards the future skills is your schema evolves over a period of time. You update a file, no retraining or no redeployment. That's the direction the industry is moving. So yeah, with that said, we can jump into the demo. This is the agent that we built in. As we see, it actually we're injecting the context and domain awareness to this. So in a sandbox, this is a demo graph that you can actually say what kind of labels. It gives you a summary of how many schemas, data sets, and breakdown of that. We can actually talk to the agent now. It's actually making a call to Claude and say that how many labels exist on this, and it actually executes successfully and gives you that the core label of C10 has been applied, and it translated into a natural language which says the sandbox contains a single governance label. This appears to be a core classification label, likely part of all the details about governance data within the best graph. We can also do an inspect graph. Now, this is where I was trying to do explain earlier. This breaks down into multiple queries and gives you the see how the reasoning and translation of that into 8 different queries behind the screens, and it gives you how many entities count of this graph, where what are the relationships for each query. It actually reasons, acts on it, and translate the results as well. Like the graph contains 65 relationships and what types, We can go through the count of individual breakdown of the entities across different types. What it actually gives you is also the out degrees, like how deep and wide is the graph. This gives you a visibility of which entity ID is like kind of having the out degree, the max, and have insights on that. So engineers or data stewards can act on it. Or we also have other queries, including the labels, how many labels is generated, and then what options are option labels. So this is all a context driven, specific to this particular sandbox. So this is the thing that we built on top of it, and we got a eight pre-built or queries that we did on, and then we have this summary coming up like this at the end. That's what we built on top of it. Right now, now I'm yeah, I'll pass it on to William now. That's the demo that I had for what we built.
Hey,
Over to
Murthy,
you.
there's a question in the chat. I think you might be able to answer better than I can.
Thank you. Are there universal cipher skills you're using starting point to generate the queries? We're actually passing on, there is no generic queries, but we are actually passing on the context. We are injecting the context and the schema, like, for example, governance label. We're making the LLM prompts via our injecting at the runtime. So we're not doing a generic or a universal queries that we are using. More towards we just injecting the graph, the schematics of the graph. For example, governance label or policy to make this LLM enable or the agent enable to answer the questions in the context. Any other questions on there, William? Do you see any other?
I think that's the only one I see right now.
Okay.
Oh, here's one more.
Yes, another one. Are you generating a schema using an LLM or an algorithm? We are actually generating via our own algorithm. So the LS, so it avoids us to keep the context intact and not depending on LLM's hallucination. So we do it with an algorithm. For a good question. Oh, maybe there's another question, William, you want to take it? I dropped this in QA. Can you provide some practical examples of the movement to lean nodes, properties you converted to nodes?
Yeah, I'll share again. Hang on, let me find that slide. Give me 1 second. Okay. So I think basically, I'll try to explain it briefly, and this might be a little redundant from what I said earlier, but if you imagine previously these brown, pink, and green nodes were all self-contained in these entities. So what we previously had to do was, in order to discover, say, a specific property for a brown node and a pink node, we would have to traverse the graph by entities, or if we had to search for it, we had to search by entity first and then introspect into the specific properties. So we couldn't, we effectively didn't have a straight way to get at the properties without going through an entity node. So it's a very roundabout way. So we couldn't directly get at it. We couldn't traverse by it. So by exploding it out, it gave us a lot of flexibility. So we can query these properties directly without having to know the specific entity it belongs to. And then we can essentially identify paths between specific properties without having to go through an entity. I don't know if that answers your question, but that's sort of like a really quick way to explain it.
Hey, William, there is a follow-up. Could you want to take that
Can you
in
read it
detail?
for me? I'm sorry, I can't see the chat while I'm sharing.
Sure. Can you briefly talk about the challenges you had or thought about while trying to make this robust?
Oh, good question. So there's actually quite a few. There's probably a couple of ways to define robustness. Robustness for us was primarily in making sure the system can scale up. So our clients, as they scale up their workload, and we have an increasing number of loads. So just to support that, we basically need to be able to scale up and scale out. This is where, again, by by exploding our data model, we can make our APIs more refined and more precise, so we can get at the answers more quickly. And that's why it was important for us to essentially offload reads to make them less expensive. But again, the trade-off is writes became more expensive. So we did solve one problem and introduce another one. But to solve the write problem, to minimize the cost of it, we really had to minimize the scope of the writes. And that's essentially what I was getting to back here, where once we made our reads super performant. So getting back to here, there's a lot of ways you can make reads super performant by actually introducing more relationships, making it more verbose. So you can do shortcuts between certain properties. But of course, that creates a lot of fan out, which is what we kind of found at some point. So we actually had to figure out ways to limit the scope of the writes so that rights don't become prohibitively expensive. Hopefully that answered the question.
Yeah, I think, yes, thank you. I think there was one more question. How does this correlate to the hierarchical knowledge graph?
Um, I'm not quite sure what the question pertains to. Can you clarify?
Hierarchical knowledge graphs related to the explosion.
I think what you're trying to get at is going back to this. Oh, so that's right. Um, so
Like everything
basically,
extended
yes.
outwards. So yeah, I think this is the question. Yeah, sorry, William. Go ahead.
Exactly. So previously, all the nodes were self-contained, the graph would look something like this, where the properties weren't really surfaced. So yes, you do get an explosion of the graph where it ends up like this. So previously, we would have simply these dark purple nodes, but now the dark purple nodes are exploded out with properties that results in these orange, brown, green, pink nodes and things like that. The interesting thing is we found that with Neo4j, since they're highly optimized around this data model where you explode things out and you have all these relationships, it's actually not very sensitive actually explode this out. So it can actually traverse these relationships super fast. So actually, the more of a boast you have, the better. And it actually makes the API a little more human readable and refined. Again, the only challenge is, so obviously if this was super verbose, reads are super fast. We can shortcut things, say between this pink node and this green node super easily. Again, the challenge becomes like, how do you maintain all these different relationships? So say I want to maintain a relationship between this pink node and the various green nodes. An update here will fan out to these purple nodes, fan out to the green nodes, which may fan out right from the green nodes to the brown nodes. So that's what I mean by the fan out effect. So you have to kind of find a balance between managing how much the sort of minimum set of relationships you need to make your reads super performant without making your writes basically cost prohibitive.
I think there was another question. How do you evaluate the effectiveness of the graph schema? How do you test if the entity and relationships extracted are correct and relevant to the context? Yeah, that's a great question. So I'll take this, William. So we evaluate schema effectiveness through performance and parity. We look for index-free adjacency, ensuring or making sure traversals don't turn into full scans. We use structural equivalence testing during the migrations that we ran, and for the AI agents, we use schema awareness. If the model can consist and generate 100% accuracy, that's how we test it. So it's the correctness is basically a cipher without hallucinating about the labels. The schema is contextually relevant. um, so basically, we also, if you've seen for debugging, we have enabled and we have a feedback loop as well, um, where we enable the logging of the query, what the query was generated, and how relevant is it to the question to get the feedback on. I think there is an question, William. What is your comment on creating index with respect to having external properties and entities self-contained?
Okay, let me share again. Maybe I wasn't, I think this is a question. I think you were trying to ask what I mean by exploding out the, so previously all these, the brown, pink, and green nodes were completely self-contained in the entity itself. So if we go back to this earlier diagram, these rectangular nodes that represent the properties were actually contained within as properties in this node. So imagine in CosmoDB and a document DB, these are all just single documents where all these properties are in there. And that's what I mean by self-contained. So we now explode out the properties. So all the properties are distinct nodes. So this entity actually doesn't contain any property in itself. It points to properties. So
I think there is a follow-up or a couple of follow-ups. Are you doing any schema prunings about that? And then the follow-up is now how to allocate in indexes of the two different approaches to property attachments. This affect the rights expenses trade-off.
okay, let me address the first one first. I think the question around schema
The
pruning
pruning.
is
Yeah.
the graph schema itself. So the graph schema itself is effectively defined and is a prescribed workflow. So it's not something that changes over time. So we basically set that in stone and we use that as sort of the model for which how the workflow, the AEP workflow should work. So it's essentially set in stone. So that doesn't change. The second question, let me see. How to,
I'll read it out for you again, William. So it was a follow up from the previous. How to allocate indexes of the two different approaches to property attachment. This affect the rights expensive trade off.
yeah, exactly. So that's where we actually leverage Neo4j's help in identifying how to essentially create so we actually started with our initial attempt at creating the data model and then indexes, and we iterated over that with Neo4j directly. Fortunately, we were mostly on the right track, but again, it was just through iteration, working with Neo4j directly on that. And I think that's probably the best path, starting with an initial data model, an initial set of query establishes the your specific criteria and requirements, because Neo4j won't know that, but they could certainly help refine that once they know what you're trying to do.
There's one another question we are on top. I'll quickly answer. You talked about exposing the schema and graph to agents to ensure coherent reasoning based on the graph. In order to properly lead the agents to reason over graph context, what other info about the graph did you have to expose? Community summaries, example questions, you can answer. This is a great question. We call this as an agent's context map. To move from a normal query generator to a reasoning agent, how to build the agent, we pass three additional layers of graphs metadata: the topological statistics, the cardinality, and the depth. The schematics, the golden path. We provide curated cipher templates like scales. There are example query patterns for complex domains, or like calculating effective permissions, and domain guardrails. Basically, we define the intent of the relationships. For example, telling the agent that inherits is transitive and directional. This prevents the agent from traversing the graph backwards or making logical errors in policy enforcement. That's what we call it as a domain guardrails.
Oops,
We
we
expose
lost your. Go ahead.
finally we expose the capability sampling. So in short, we don't just give it a structure, we give it the topological map, and the domain playbook too. That's how we give for thank you for this great question.
Okay.
I think we're at the
Yeah, I
top
think we're
of
at time. I think Hannah's giving us the signal to
the
wrap
last
up.
question. Varun,
Go-
yes, we are storing we are storing the long-term memory, and yes, we are on the chat history. And we also built a feedback loop to see how it is performing for our analytics. Thank you, Warren, for that great question. I think we're running a little over, so feel free to hit us up, or and further questions we'll be happy to answer. Thank you so much for the active participant.